Hello, my name is Past Paper Guy. Today I'm going to be solving the AQA A-Level Physics Paper 1 from 2017, and I'm going to be going through question by question, blow by blow, exactly as you'd need to in an exam. Hopefully this will be useful for your revision. If it is, then please share it with your friends and like the page. Thank you. So we'll start with question 1. Isotope potassium 40 is used to date rocks. It decays by electron capture. So they're giving you most of the equation here. Nice easy one to start off with. You've got to make the numbers balance, so we need an 18 on the bottom, 40 on the top, and here we need something to balance the lepton number of this. This is a particle, so we need an electron neutrino to balance, and it's got to be the neutrino, not the antineutrino, because that's a particle, not an antiparticle. Which fundamental force is responsible for this decay? So it's the weak force, and the reason it's the weak force is because it involves more than just hadrons. Strong force only acts between hadrons, so this has both hadrons and leptons, so therefore, because it involves hadrons and leptons. Okay. And that's the only force that does so. One decay mechanism for this results in having an excess energy of 1.46 MeV. It loses energy by emitting a gamma photon. Calculate the wavelength. So this is E equals HF, which if you look at the formula sheet is located there on your formula sheet. We're going to want this version of it because we're going to want to find lambda. So which is the same as h c over lambda. Rearrange for lambda, and we get lambda is equal to h times by c divided by e, which is, well, h is 6.63 times 10 to the minus 34. That's on the front page of your formula sheet, which is located there, Planck's constant, times by 3.00 times 10 to the 8th speed of light. It's also on the formula sheet. Leave the formula sheet here, which is there. And then we need to divide that by the energy, 1.46 times 10 to the 6th to get mega electron volts, but then we need to change this into joules, so we need to times by the charge on an electron, which is somewhere around here. There it is. 1.6 times 10 to the minus 19. So all of that gets shoved in the calculator. 6.63 times 10 to the minus 34 times by 3 times 10 to the 8 divided by all of this, 1.46 times 10 to the 6 times by 1.6 times 10, times 10 to the minus 19. And that gives you a wavelength. It's pretty small, which is what you'd expect from a gamma. So everything is to 3 significant figures, because that's written to 3SF here. So we can write this to 3SF. So 8.51 meters to 3 significant figures. Okay. Right, question 1.4. Then the potassium isotope can decay by second emission process to form calcium 40, which is this. So the equation for this would be 40, 19 potassium goes to calcium 40 plus an electron, and then we need to balance lepton number again, so we need an anti-electron neutrino to make that work. Okay, so this is the other possibility. It's worth writing that down. I think actually on the mark scheme there's a mark for it as well. So what we're doing is, how can we confirm which process is occurring? Well, we either need to look for these, or we need to look for these. If we find these, we know this one's occurring. If we find electrons, we know this one's occurring. So look for gamma photons or electrons if gamma photons are emitted, then it is electron capture. If electrons are emitted, it is beta decay. Right, so how do we find electrons? So beta decay would, for example, there are lots of ways you could find electrons. One way is that they would discharge a positively charged electroscope. So beta decay would discharge a positively charged gold leaf, can't spell gold, leaf electroscope. So that's one of these things. It's when you've got the plate like that in the box, you put positive charge on there, and then if you fire electrons at it, it will discharge. If you've fired non-charged particles at it, it would stay the same. Second thing we could say is how we could detect gamma photons, because it says here how could we confirm which process is using. So gamma photons would expose photographic film through 2 millimeters of aluminium, whereas an electron wouldn't do that. It wouldn't penetrate the 2 millimeters of aluminium. So what we got here, we've got the fact that it's beta decay is the second possible reaction. We would either look for gamma photons or electrons. If we found gamma photons, then it's electron capture. If we found electrons, then it's beta decay. Beta decay would discharge a positively charged GLE, and gamma photons would be able to expose photographic film through aluminium. Okay, question 2. We're going to be doing this experiment here where we're stretching a string. You should have done an experiment like this, creating waves on this string as standing waves, and then working out what frequency the first harmonic is at. We got this data and we're trying to show that this is true. So we should remember that's the weight there, which is identical to the tension in the string. So the tension pulling this way is going to be equal to the weight that you add there. So tension is proportional to the mass by the constant of gravity. So all we need to do then, if that's the case, then that means that the force is also proportional to the square root of mass, which means that in that case, then if we have the square root of the mass and we divide it by the force, we should get the same number for each one. We should get a constant. So we're just going to work it out for each example. So we've got square root of 0.5 divided by 110, the square root of 0.8 divided by 140, and the square root of 1.2 divided by 170. And we need to work all of those out. So we've got root 0.5 divided by 10 is 6.43 times 10 to the minus 3. This one, root 0.8 divided by 140 is 6.39 times 10 to the minus 3. And here we've got the square root of 1.2 divided by 170, so that's 6.44 times 10 to the minus 3. And all of those are the same to 2SF, so therefore it holds true. So they're all 6.4 to 2 significant figures. Right, here we have a nylon string used has a density of this and a uniform diameter of that. Determine the length of the string used. So we're going to be using this equation here. The first harmonic, F is equal to 1 over 2L times by the square root of T over mu. Okay, now let's see what we can do here. If we have a bit of the nylon thread, like so, and we think it's got a length of L and a cross-sectional area of A, mu is equal to the mass of that divided by L, the mass per unit length. Now if I times on the bottom by the area, then the area times by the length there is equal to the volume, and that quantity is our density, rho. I can't just times the bottom by A, I've got to times the top by A as well. So that's equal to rho A. The mass per unit length is equal to the density times by the cross-sectional area. So let's work that out. We've got the density is 1150, that's in meters, times by, we need the cross-sectional area, which is pi times by r squared. So r is, just be careful because that's a diameter, so we need to halve it, 5.0 divided by 2 times by 10 to the minus 4 squared, like so. So we need to work that little bit out. So I'm going to do this bit first. So that's 2.5 times 10 to the minus 4, just divided that by 2. And we square that bit, we times it by pi, and then we times by 1150, and that gives me 2.258 times 10 to the minus 4. That's kilograms per meter. Okay. Right, so we've worked out what mu is. Now we need to use the rest of this formula to work out what L is. So we just rearrange for L and we get L is equal to 1 over 2F. I'll just switch those two around. Square root of T over square root of mu, which was that. And we know all these now. So we just need to pick any value from here. You could also average these values if you wanted, but it doesn't really matter in this case because they're all so similar. So we've got 1 divided by, I'm going to just choose the top one, 2 times by 110 times square root of tension, or tension is mass times by gravity, so it's 0.50 times by 9.81 divided by the square root of mu, which was that, 2.258 times 10 to the minus 4. Right, so bring the calculator back in. I want to do that first because it's in my memory at the moment. So I've just worked out that. I want 1 divided by it. Then I'm going to times by this first. So that's times by the square root of 0.5 times by 9.81. And now I need to divide by this. So divided by 2 times by 110. I usually break up the calculations into smaller chunks like that. I find it easier to do than typing it all in one go. Some people are different, they prefer to type it all in one go. That seems about right, because that's in meters, so just a bit longer than that really is going to be the length of the string. So that's 0.672 SF, and the units are meters there. Okay. The student uses a relationship to predict frequencies for the potentials that are much larger than those in the original experiment. Explain how the actual frequencies would be different to those that the student predicts. Right, so if you use something that was much larger frequency, then that's the same, so therefore T will be much larger. So it's going to have a much higher tension. The tensions will be very high, Okay, so now we've got a very high tension. What effect will that have? Well, if we have a very high tension, it will tend to stretch the piece of nylon like so. If we stretch it, we make it longer, and so mu is equal to the mass divided by the length, so that will reduce mu. So this will reduce the actual value of mu, right. So if the actual value of mu is reduced, what will happen to the frequency? The frequency would be higher because mu's on the bottom there. Thus, the actual frequency would be higher than calculated. Okay, so because the nature of the experiment is it will stretch the piece of wire, that will reduce mu, which in turn will increase the frequency that you measure. So the frequency that they calculated using a fixed value of mu, well, mu will actually have reduced, and so therefore your frequency will be higher when you measure it. That's the end of question 2. Question 3, here we have our refraction question. So the angle of refraction is 90 degrees. So this is Snell's law. So the easiest way to do Snell's law is like this. Now that's located on your formula sheet here. Now I know there's this stuff for critical angle, but frankly I'd always ignore that and just always use this. It's just easier just to use one rule for everything. So we just put in the values. This is one material, this is another. Let's say this one is glass. So we have n, which is 1.6 times by sine of theta 1, which is what we're trying to work out, is equal to n2, that's air, so that's 1 times by the sine of that angle there, which is 90 degrees, sine of 90 is 1. So theta 1 is equal to 1 over 1.6 sine to the minus 1 of all of that. So we do, wrong button, shift, sine to the minus 1 of 1 divided by 1.6. The lights just decided to turn off. And we get this answer here, which is 39 degrees to 2SF. That's the 2SF, so that's really as good as you can do. Right, we change the situation a little bit. Instead of going into air, we go into this liquid, and now we've got an angle there of 58 degrees. Dead easy again. N1 sine theta 1 is equal to N2 sine theta 2, exact same equation. So we've got 1.6 times by sine of 58 is equal to N2, which is what we're trying to find out, times by sine of 90, which is just 1. So N2 is just equal to that bit there, which is 1.6 times by the sine of 58. So N2 is equal to 1.4, 0.3568 dot dot dot. No units, of course, for a refractive index because it's a ratio of wave speeds. Right, this question here now. Now, my personal feeling is that they made a mistake when setting this question. They expected one answer, but actually there are 3 possible things that can happen. So let's just think about what they are, and all we need to do is come back to this equation here. So we have n1 sine theta 1 is equal to n2 sine theta 2. So we'll have this as the glass and this as the liquid. Right. What we're going to do is I'm just going to divide through by this. So we've got n1 over n2 times by sine of 58, because that remains constant there, is equal to sine of theta 2. So when these two for green light, then this comes out at exactly 1, and so therefore we get 90 degrees coming along here. Now, what they've done is they've said that if you go to red light, it has a low refractive index, and blue light always has a higher refractive index than green light. So let's do blue light first. So we'll do for blue. Well, what happens? Well, if they both increase by the same amount, so let's say they both increased by 10%, so this refractive index here and this refractive index here are both increased by 10%, then those two will cancel and we'll get exactly the same thing happening. That's not what will happen, but we don't know how much they increase by. So blue, if they both increase by the same proportion, then it is exactly the same. Right? If this one increases by more than this one, so if glass increases by more than the liquid, if glass increases by more than the liquid, then this will be so this fraction here will be slightly bigger than 1, so that will mean that that's impossible to do, so it will get total internal reflection. And if this one increases by slightly less than this one as a proportion, so if glass increases by less than the liquid as a proportion, then that will be slightly less than that one, so we'll have all of this will be slightly less than 1, so that will be an angle that's slightly less than 90 degrees. Then it will refract at less than 90 degrees. And the same for the red light, but the opposite way round. That what will happen is if they decrease by the same, they'll cancel out and the exact same thing will happen. If they decrease by 1, you'll get total internal reflection, and the other way up, you'll get refraction. So this was a really badly worded question. I think, see, they originally had the idea that the blue light would totally internally reflect, the red light would refract, and the green light would be on the critical angle. But you can't tell that from the words here, and so they had to accept the complete opposite of that, in fact. And this is the explanation, and it's because it depends on how much these change by proportionally to one another. So if you didn't really understand what was going on in that question, I don't blame you at all. It's a badly worded question on their behalf.